When we analyze a divide and conquer algorithm, we are watching a single computational problem aggressively fracture into hundreds of smaller, identical pieces. Evaluating the exact time complexity of these expanding structures usually requires drawing out extensive recursion trees or using the substitution method. Both approaches are mathematically rigorous, but they take a lot of time to map out by hand. We do not always have to calculate every branch manually. There is a definitive, constant-time mental shortcut designed specifically to bypass this bottleneck. It is called the master theorem. For a specific class of recurrence relations, this theorem provides the exact mathematical time complexity in seconds. This equation on screen shows the entry condition for using the theorem. T of n equals a times T of n divided by b plus f of n. This specific format mathematically represents the standard behavior of almost all division-based recursive algorithms. To use it, we are going to decode the anatomy of this formula, establish the critical mathematical comparison at its core, and run tests on its three foundational cases. Memorizing the structural anatomy of this equation is the prerequisite for avoiding manual tree drawing. This graphic isolates a concrete example of our formula in action. T of n equals 4 times T of n divided by 2 plus n. The variable a tells us the exact number of subproblems generated at each step of the recursion. The variable b is our size reduction factor. It indicates how much the data shrinks inside each of those new subproblems. And f of n is the non-recursive work performed at that specific level, the effort to divide the array or merge the results. This diagram of a balancing scale illustrates the engine of the master theorem. It operates on a strict mathematical comparison between the non-recursive work on the left and a new expression on the right. That expression, n to the power of log base b of a, is the mathematical representation of the total number of leaves at the absolute bottom of the recursion tree. The core rule of the theorem is that the final asymptotic time complexity is dictated entirely by whichever of these two sides grows faster. Applying the master theorem requires only calculating that leaf quantity and comparing its growth rate to f of n. This calculation matrix introduces our first test case. From the recurrence, we extract our variables. A is 8, b is 2, and f of n is n squared. We calculate the critical leaf quantity by taking log base 2 of 8. Log base 2 of 8 is 3, which simplifies our exponent to n cubed. Returning to the scale, we execute our comparison. With n squared on the left and n cubed on the right, the scale tips heavily toward the leaves, initiating case 1. Because f of n is polynomially smaller, the sheer volume of recursive leaves at the bottom of the tree mathematically overwhelms the non-recursive work. Whenever the leaves dominate the scale, the final time complexity is strictly bounded by those leaves. Our answer is theta of n cubed. This new matrix shows the standard recurrence relation for the merge sort algorithm. Here, a is 2, b is 2, and f of n is simply n. Calculating our critical leaf quantity, log base 2 of 2 collapses to 1, yielding simply n. We check the scale. With n on the left and n on the right, the two sides balance perfectly. This is case 2. When growth rates are identical, computational work is perfectly distributed across every level of the recursion tree. To resolve case 2, we take the balanced quantity and multiply it by the absolute height of the tree, which is bounded by log n. Merge sort achieves its famous theta of n log n efficiency strictly because its recursive structure maintains this perfect case 2 balance. This final matrix tests our third recurrence. Our a and b are both 2, but our f of n is now n squared. We execute the calculation for the critical quantity, yielding just n. On the scale, we compare the heavier non-recursive work of n squared against the lighter critical quantity of n. The scale tips heavily to the left, triggering case 3. When f of n is polynomially larger, the heavy lifting performed outside the recursion dominates the algorithm's total runtime. In this scenario, the algorithm's final time complexity simply adopts the dominant f of n term, resulting in theta of n squared. This decision matrix consolidates the entire master theorem into a single, scannable framework based on our critical comparison. If f of n is smaller, the complexity is the theta of the critical leaf quantity. If f of n is equal, we append a log n multiplier to that same quantity. And if f of n is larger, the complexity is simply the theta of f of n itself. Internalizing this grid replaces grueling algebraic derivation with a deterministic, repeatable algorithm for human analysis. This split screen highlights a critical warning. The master theorem is not universally applicable to all recursive functions. The theorem strictly relies on n being divided by a constant factor b at each step of the recurrence. Subtraction-based recurrences, which are frequently found in dynamic programming or basic recursive counters, break the theorem's foundational logic. For these incompatible formats, you must revert to the substitution or recursion tree methods. When boundary conditions are met, the master theorem instantly resolves the complexity of divide-and-conquer architectures without drawing a single branch.